Another physics video. Another physics video. Another physics video. Okay guys, so we're back at it again with another physics video. So today our topic will be power and energy. Things that we'll cover in this video: a definition of these two concepts, power and energy. We will introduce their formulas and we will derive their formulas as well. We'll have a unit analysis of these concepts. We'll include proper examples to explain these concepts, demonstrations, and other things that can help us understand power and energy. Well, that's it for the introductions. Time to get into our physics video. So, first things first, we're gonna start off with energy. So, what is energy? Well, energy is the ability or capacity to do work, or the ability to transfer energy. It is a quantitative property that must be transferred onto an object in order to have work done. There are many types of energies. There is potential energy, kinetic energy, solar energy, thermal energy, gravitational energy, energy where you lose your sanity. Energy is something that can only be transferred. It cannot be created nor destroyed. Because of this, we have something called the law of conservation of energy. The two types of energy that we'll be covering in this video is gravitational potential energy and kinetic energy. So let's start with gravitational potential energy, or EG for short. So when we talk about gravitational potential energy, we refer to height. Therefore, we would need a reference point. So gravitational potential energy would represent the potential an object has to do work because of gravity. An example of gravitational potential energy in motion is if you were to take a ball and drop it at some random height. When the ball falls, it falls with gravitational potential energy because the only type of energy being affected by it is gravity if you neglect air resistance. So the formula to calculate EG is EG equals to mgh. So how we get this formula is that we know work is equal to FAD cos theta. FA being the force applied on the object, D being displacement, so how far the object moves, and cos theta being the angle between these two factors. So because cos theta is equal to 0, there is no angle, so it equals to 1, we can ignore that factor for now. So the only thing left is FA and D. The only force that's acting on the object is gravity, since it's gravitational potential energy. And then displacement would be the height, or how high the object falls down. The unit measured for EG would be joules, because joules are a unit of energy. Now let's move on to kinetic energy. So kinetic energy, unlike gravitational potential energy, is energy possessed by an object in motion. So while the object is moving, there is energy being transferred onto the object. A big factor of determining an object's kinetic energy would be their velocity. So we have the equation EK equals 1/2 mv squared, or EK equals 1/2 mv2 squared minus v1 squared. We derive this equation from our work equation, W equals FAD cos theta. So, because there is no friction, we have W equals F net d cos theta. Now, instead of F net, we can just change it to W equals MAD. Now, using our kinematics formula, we can replace AD with V2 squared equals V1 squared plus 2AD, and then we have the V2 squared minus V1 squared over 2 equals AD, thus giving our original formula. And again, kinetic energy, like potential energy, is measured in joules. Now here, we have two inclines, A and B, and a ball at the end of each incline. Now let's assume that both these inclines are at the same angle and we drop both the balls at the exact same place. Now which ball would reach the end first? Would it be A or B? Now a lot of you might have chosen A because in B, there is a slight incline after the small decline. Now if you think that incline was enough to stop the ball from reaching the end before A, you were wrong. Haha, fooled you, loser. Can't do any physics, lol. Now let's explain this phenomenon. So although B has an incline, there is also a decline, and when the ball goes on the decline, the ball will gain kinetic energy until the incline, but by then it reaches the incline, it would have already arrived faster than A. Here is a video that I recorded to show this demonstration. I made the two tracks with cardboard, as you can see, one with just a straight cardboard slate and another one with a small incline and decline, and then I put them both on the same binder so it represents them having the same angle, and then I dropped two marbles with the same mass, and you can see which one falls first. So you can see from the video that the marble traveling in the not straight track was faster than the one traveling on the straight track. Now keep in mind this is just a simple demonstration. There are a lot of factors that could cause this experiment to go wrong. For example, this experiment only works when you don't take friction into account, but since there is friction, it's not always 100% accurate, and as well as angle between the two pieces of cardboard, they're not 100% accurate as well. So this is just a simple demonstration showing kinetic and gravitational potential energy together. Now, you may be wondering, that's all great and stuff, but how do any of these relate to one another? Like, what is the correlation between all these numbers and letters and kinematics? Well, introducing Energy Lab with Astronaut Wally, preparing for takeoff, Houston. Here we have a little lab that represents the correlations between certain things and energy. So there's this little guy named Wally, and there are these bunch of buttons here that you can fiddle around with, and these control his mass, his maximum speed, force, and energy, and all that stuff. And then you can turn the on and off button, and he goes flying somewhere into the abyss. After, you can plot these points and put them on a graph, and then you can see the different correlations between work or energy and other stuff. So then I came into the conclusion that work is directly proportional to displacement and force. Energy given to an object has nothing to do with mass, and kinetic energy is proportional to velocity squared, and it is directly proportional to the mass. So from this data that we collected, we can see that these things coexist and relate to one another in a perfect physics harmony. Okay, let's move on to power. So what is power? Power is the rate of which work is done. So it's basically how much work is done over a certain period of time. So we have the equation power equals work over time, or it can be power equals change of energy over change of time. We have power measured in watts, we have work measured in joules, and time in seconds. So there are three major types of power. There's instantaneous power, so this is when you want to find the power of something in a very specific point in time. So time is usually very small. Then we have average power, so this time we have time as a larger value because it's over a longer span of time, not just at like a single point. And it can also be found with the power time graph. So as we know in a power time graph, the area under that graph would give you work done, and then when you just divide that by time, as we know earlier, P equals W over T, and that will give you power. Now there's peak power, which is the maximum value instantaneous power can have in a system. So the value you would get would be very, very large, and peak power is usually super hard to maintain because when you maintain such a large amount of power, it can usually be very harmful, or we can't sustain that power for a very long time. So you may be wondering, that's all great, so what? What are we gonna do with this? Well, let's do a problem and see how we can put this into action. So we have a vehicle, and it weighs 1,000 kilograms. And it has the power to output into the wheels 500 watts, and then it constantly accelerates up to 25 meters per second. So how long would it take for the vehicle to accelerate to that speed? So we start off with the formula that we introduced earlier on. We have P equals W over T. So we're given mass, we're given power, and we're given velocity, but we need to find time. So instead we can substitute work with our FAD cos theta, and since angle is equal to no angle, so cos 0 would equal to 1. So we can get rid of the cos theta, and then now we're left with FAD over T. So we know that D over T is just equal to velocity, so instead we have force and velocity. Force times velocity equals power, and we know force is equal to mass times acceleration, so we have P equals to MAV. Now we can replace velocity with 1/2 v1 plus v2. Now we can substitute acceleration with change of velocity over time, and then we can rearrange the equation so that P equals to mv squared over 2t. Now all we have to do is plug all our values in, so we have 500 as power, 1000 as the mass, 25 as velocity. Since it starts from rest, we have 0 plus 25 is 25, and divided by 2t. And then as we solve for this, we find that t equals to 25 seconds. So it would take 25 seconds for the car to accelerate from 0 to 25 meters per second. So we learned from this question that the larger the power, the more time it will take, and that we can use our original equation P equals W over T, and we can rearrange that with more simpler concepts such as velocity and acceleration. So we went from work over time to mass times velocity squared over 2 times time. So in conclusion, we learned throughout this video the traits of energy, the formulas, kinetic and gravitational potential energies, and things that influence energy. We also defined power, and we had a formula for power and examples of other ways we can use that formula. And yeah, that's it. That's it for the physics video. Hope you enjoyed and you guys learned something. See ya.